Okay, start of my clock. So, for 5 minutes time, down this clock. This is finish time. It's, so basically, time now is 4, February 2026. The date is 7. Time now is 10:47 a.m. We got last color. So, set up a bike. Um, so I'm gonna have to do something instead. But I got my notes here. So I'm gonna read this thing here. I'm gonna continue from there. So hypothesis: quantum supershift and entanglement via graph current measurement for measuring memory mosaic system or magnetic measurement system. So you're gonna have a kind of reader, a disjoint reader and writer, or two system double scale for kind of system of topology via topology. So you're gonna have a planar unilateral planar topology. Basically, what does that mean? Unilateral, meaning of an action or decision performed by effective one person, group, country involved in a situation without agreement of another or of an action or decision another or the same. Basically, it's uh, uh, permissive sector, on basically consensual unilateral non-polarity. So bipartite. So you're gonna have like unilateral on the lateral polarity. Basically, you need two parties to do it of an action to do something. Basically, it's an inverse observer. So you're gonna have a bipartite graph current, polling. Bipartite just means two systems, entities, two somethings. Polarity means how it's organized, and a system of non-linearity. You're gonna have system of polarity. So you're gonna have. I'm gonna define this formula in the framework of the problem, but I have to do some drawings too. So let's say you have an 11 graph, an 11 walk, 11 path. So you're gonna have. A model going to give you a state of via a qubit. So it's going to be a comprehensive model to comprehend. But we're going to try to do on paper first. So I've got the system, the kind of color coding behind me. And you have to do it properly. So you have to do it properly. So you're going to have to try to do it properly. So you're going to have a system of, you're going to have a bipolar system. System with two poles. But these are two poles that are unilateral. So you don't share any connection, you share anything. Because you want to disconnect without being so you're gonna have connect, disconnect, connect. So you're gonna have connect, disconnect, and stuff from there. But you don't want any explicit disconnect. You just want to always connect. So you want to always wait connection. So it's you're gonna basically have no disconnect operation. But this connection operation is gonna feel so you're gonna have double zero. So connect if you can connect to something, you can disconnect the two poles on the system. But the two unilateral poles. So you just want connection. You don't want connection. So connection defined by noise in the environment, no noise in the environment, and no signal. Basically, the cases of test rules. So, you're gonna have noise environment, like a random generation of something happening in the environment via quantum spin. Quantum spin defined by the block sphere framework. So you're gonna have this kind of framework here for this, but they're unilateral. The shared consensus. You're gonna have the unilateral. You're gonna have the noise. The noise. You're gonna have no noise framework. there's no noise environment, there's no signal. That means you're no, sorry, no noise. You don't have noise, so you're gonna have no connection, no signal. No signal. You're gonna have no noise. No noise. So this is called a noise space or the computation space of object components. You're gonna have some here. So you're gonna have a quarter electron. So you're gonna have electron. So you're gonna basically have um, a model here. My model is basically this model here. So you're gonna have electron. 1 second, guys. So you're gonna have this model here. So you're gonna have quantum superposition. Tandem via Glaucon. And Glaucon is going to determine kind of vertex current of the system via Mozambique bank. This is a memory transfer. This is what focus on the state. The state. But this state is my example. This is bipartite. You can have a disjoint bypass state. You cannot recover what you don't know. So because you cannot connect yourself to recovery. So basically, I'm going to go to the board now and show you what I really mean. With system. So this is a magnetic memory model. So let me start with the board. So you're gonna have a tape. So you're gonna have an electron. On the outside here, 2 electrons. Called electron configuration, and it's called the spin. Spin basically works in halves. You're gonna get you're gonna have the block spin model of spin. So if you have a zero pipe half so do around the third of 2 square root of 3 divided by 2, you have this is the other way around. So you're gonna have this is the other way around. Sorry guys, no. So you're gonna have 0. So if you have a half of 0, if you have a half of 0, so you're gonna have I have the vector of I. But this can be this. So you're gonna have 2 states, a half of 0. North. So basically you're gonna have a north. So you're gonna use the bearing system. So you have the bearing north, east, south, west. But the polarity system, the bipartite polarity with the points, so you're gonna have numbers for them. Numbers. If you have 0.7 north, that's basically magnetized north. The pole is magnetized. The pole is spinning more to the north. There's some kind of polarity. Go to pole, the point is pointing north. But the pointing there's no pointing. So you have the conjugate model. So 0.7 and 0.7 you got the north. If you point it, they have east. If it's pointing east, 0.3. 0.3 east 0 point. So you're gonna have 0.3 east to make one whole unit of the system. This way the share in the bipolar system. This is the way. So for example, you can say 7 of 0.7 0.7 over 1 I plus 0.3 over 1 I. These are 2 units 2 over 1 J. Of J. J mean the J hat of the vector, but the J hat is what is share over 0.1. So 0.3 is in giant J. These are dimensionless quantities of a system. The system of polarity works in dimensionless quantities. So you cannot have something like something of a system rate because it is bound by kind of a mixed fraction model. The improper function transferred to this amount of what the process does is you can have 5 over 1, 2.05, 2 times 2, 0.7 over 1, and 5 plus 0.3 over 1 J. But this is the J hat. J is the hat, the unit of 1. So the unilateral shares consensus over bipartite systems. 2 or more systems working together to achieve a consensus that we need to keep that channel coherent. So the model is based on electron spin. So electron has negative charge, but the spin now obviously they have a bipole of position and velocity. So there can be a place because it spins so fast, the spin around the nucleus and the proton nucleus and the proton You know, they have kind of spiraling they do into the basically basically they have a position of velocity as each and that's gives the quantum. So you can only determine a system when you measure, which you can measure. By that measurement is an observer. So if you're an observer of a system, you can measure something, and that's then pops into reality. But that reality is your shared reality. So you're sharing that something. So you want to connect to something you're sharing. You're showing something you're showing to accept. Doesn't matter what I'm looking at. What I'm if you take a measurement of a system, if you polarize something, you are literally given a position. So if the position is like x y z coordinate, x y z coordinate. No, no. Let's say x squared plus y squared equals t squared. I get a x squared plus a s squared plus by plus c equals 0. You have the quadratic equation. I keep mentioning quadratic equation, but I'm not really using it. Negative by y equals negative square root of negative a plus or minus square root of b squared over 4ac over 2a. Okay. So you have the kind of system here of linear not unilateral. The time dilation equation for Lorentz factor depends on time and space. So you can measure something in time, but the axis is basically the dimensional axis. So you're gonna have I a sub I a sub I a plus b sub I equals c. Because the dimension of which is split the a sub I plus b equals no, a is the coefficient plus b sub I equals c. Because A and B share dimension quantity as alpha numeric systems. They work at alpha numerism. Because if you add a dimension and the system collapses into a state of chemicality, they share that state. So I've got my proof solution model here. Let's begin. So, here I wrote 0.5 here. So you're gonna have a proton, neutron, electron. But the electron neutron is magnetic. So you're gonna have two protons here. I've drawn. You have a topology, you have a mass. But this can be determined by measurement. Doesn't matter if the quantum spin or not. The quantum spin is basically measured in time. Time. Basically you got the theta. So you got theta. The quantum spin is theta defined as theta. And theta is always in between time to the power of -1 b divided by a. So I'm gonna set some values to this and try to do it properly. Don't care how long it takes me. I just have to do it properly. So theta defined as equal to tan to the power of -1, which is consensus of shared reality between b and a, where b is a squared ax squared plus by plus c equals 0, and s squared plus y squared equals t squared. What is the time? Now time is basically t equals the change in t equals 1 divided by 1 over 1 divided by 1 minus I'm not busy. Sorry, but I'm busy. Busy. Yeah, yeah. Lorentz factor. Yeah, I'm busy. I'm busy. Thank you. Lorentz factor. So you're gonna have the beta, where v is the speed of light, and c is the beta is v divided by c. So beta is v is the velocity, and speed, and v c is the light speed. V is the speed of the atom. So you understand the motion multiplier, special relativity, determines the magnitude of the time dilation and length contraction. But this is a formula you're gonna use to understand it. So we have work to do today, but this is the main so x squared plus y squared equals t squared is the time dilation. And you can pick a point in time to measure this kind of. So you can basically the time dilation allows you to integrate over the space too. So you can get space from time. From time. So B is the beta, but I'm trying to understand how to use this. So I'm gonna try to use the Lorentz factor theory to watch this video. So let me just stop watching this video right now. I can see what this is. This is Academy. Show this. another ad, another ad. It's annoying when you got two ads here. So I'm gonna play the video and try to. Okay, so okay, so this is a high effects. High effects. So let me just switch the camera. I don't even know how this works, but let's see how it works. I haven't done high effects in a long time, but let's see how this works. So I'm gonna flip my camera to the system state here. Yep. So T prime is gamma because T time is the integration of time, and that's T prime is gamma chain of time. So basically, this time direction, this is one chain of gamma. T prime, which time is derivative of time. So far so good. Yep. So if you move a fraction of the chain, so that's how you rearrange it. So this is if you move a fraction by t, yeah, yeah, yeah. Basically, t squared is a factor of t. So you get half the time, but this half the time is the square root. So I would agree. So because if you take a third of it, you should get t. And t is chain of t. So okay. So yeah. Okay. So this is velocity out of time. Yeah, see, the truth to this kind of for it to this, because basically the electron spins around the proton and the neutron, so they are in a they are in a stable like they don't collapse into the uh proton or neutron. They don't collapse into the nucleus of the system. So it is true. So it doesn't matter whether it's slow or fast. The stability, relatively, because relativity, the rate effect of the is small because the correlation between the space the electron holds and the time the user spends, is kind of literally in a kind of way of sort of one. So it has to spin at doesn't last speed. It doesn't want to speed of if it's a relatively fast speed, it's relative to the kind of the mass of the proton and neutron. So the effects are literally really small, relative like, but this relative this is like time dilation principles or 101. So you can understand that unless the electron spirals into unless the electron spirals into the nucleus. It will spin around, and it start to decay. I think that's called decay. I don't know what that's called, but you get electronic decay of the actual atom. Because you have energy released, and you get radiation. I think I'm gonna call it electromagnetic decay. Electronic decay. Yeah. How do you use this question? How you gonna do this from gamma and beta? Oh my goodness. So, it does work as intended. So this is just a bit, so it does work. So this is no problem. So, if equals zero, stationary, y equals one, basically change is one, the constant speed is one. So, you got if equals 0.8. See, so you can see, so basically, example values. Oh my days, I'm glad to see I got all this thing. So, so you're gonna have, dimensions quantity, especially related, how much bit of time left over this, thing. So you're gonna have, time dilation, of an actual team, so if for example, yeah, this here is right, I'm just relearning this. If for example, if 0.8 constant, then you get the 1.6. It's going to 1.6 within 1 minute. On the spaceship. Oh yes. So you got the person that goes in space, and the person goes in space and come back at the same age, say like 6 years old, and the age is different because they're aging based on relativity. So basically, it's special relativity, and it has to work on the principle of magnetic. I don't know, but it does work. It does work because it's relative physics. It's relative physics. This is environment here. So so you're gonna understand that if you have someone here, so goes in space, some kind of a spaceship or space shuttle, they go to space, they come back, but they come back at a different age. So that's how the main problem is. The position of listening is lost because you have there's some well you can go so okay, basically let me just get the translation. Let's see what the so I'm trying to calculate the polarity or sequence, so the kind of polarity or special relativity. So I'm gonna put it into I just found them, like it, but the system I'm gonna say is everything is a half, so the scale is a factor of integral. So so I'm gonna say, so I'm trying to do a computation over sine. So sine, so if you get 0.7, you get the time dilation of the factor in time for x squared plus y squared equals t squared. So x squared plus y equals t squared. S is dimension. X was d squared is a dimension. The time, the decay, and the mu and decay. Yes. Basically, mu and yes, I was right. So the upper should decay before reaching the ground because the travel near light speed, of dilation is not to the detection of SFS. So let me go here. So let me copy this. Let me see what this says. Let me see what it says, because I don't think we're able to solve this problem or even identify it. It sounds like a block square cube graph for kinematics. You essentially from a bipartisan state covering of how the relationship between the position of relation spent under relative contract. Here's the breakdown. Your model, changing theta, equals yes. As we said, you're using y as a bridge between states, the data, and the measurement. The observer, when you are see the measurement, you integrate with space. You are touching the deep through the state, the measurement, the minute square root. This relative just for looking in spatial relativity, time and space are separate. They're interdependent on velocity. You mentioned the states of north and south in quantum bipartite system. The block represents space if you look at the spin of orbiting the nucleus, this is a point. It's about the vector probability vector. The probability of united relativism describing some of the step noise, for some disconnect, of the decoherence, the relative to the transformation. If you have a party system, they become crucial for party A, party B. The clocks are measured spin versus joule from the S circle S squared plus Y equals T squared. A squared plus B squared equals C. When you're trying to combine relative phase, if the relative spin is a memory, there is a time taken for the spin, essentially from relative quantum the J hat system presents the transmission over state with a non-Euclidean geometry. There's a polar geometry. So you notice that they don't collapse into because the spin of velocity stabilizes. By the stability of information memory is a function of the resistor to help move this board. Would you like me to refine the position of map the both components? So this one spin how about remain. This one I need this to not the blockchain. I think I have to give another try. So, I'm trying to take a measurement of the two systems. So, I'm trying to take basically, I'm trying to take two qubits and spin them into using a measuring movement system. So I'm trying to solve Unilateral. So basically go to the board now. This is really got it, guys. I need to do more work, guys. So basically I'm trying to have a Unilateral system. So what it means is I'm gonna go to the board now and show you guys. No, I'm gonna do it here on my paper. So you have yellow, yellow. So you have two qubits and they have a spin, but the spin is they have so you're gonna have red red for red shift, blue for blue shift, and yellow uh, uh, green for green shift, and green here. It's gonna have green shift. So you're gonna take colors of green is basically auxiliary. So you're gonna have a combination of yellow to green, yellow to blue, yellow to red. But this conjugation machine gonna have a space of pi over 4, pi over 3, pi over 2, and pi. So the redshift model basically if something's moving away, if a measurement is taken and something that's drifting, it's red. It's red by color, So your graph is red. So the graph is red, literally. So basically, the bar part of the graph is red. I'm gonna do this red. Yep. So the bar part of the graph is red, and it's red for region. So I'm gonna just switch to other one. So it's red for a reason. So it's like it's red for a reason. So it's not that it's wrong. It's red for a reason. So you're gonna get the red color really means something. So you're gonna have a bipartite graph color. So basically, the red is from signals that is move the way drift from the system of dilation, and you get blue. Blue. So complementary of red. Complementary of red is yellow, yellow. No, no. Basically, red is yellow. Red is green. So green is coming closer, closer. So this is the measurement of result. Measurement of result. So measurement of something moving away that is an indicator of result and error is red, red, red. So red. So you can have an error. Error. The system cannot make a measurement. Obviously, it's too far away. You cannot take a measurement. It's not. You can't make a measurement. If you see red, you can't take a measure. Oh, you just get an error. You just get I don't know. You get an error exception. The result model. So like we got blue. Now the blue is opposite. So something is taking a measurement. Some other system is processing. So you can have blue indicate something is something out of view is happening. Something is happening, but we don't know what it is. So you're gonna have the exception to handle that kind of error. So you can, so you're gonna have a triadic model of a system. So you're gonna have red, green, and blue. But red, yellow, green, 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 and red. You're gonna have red, yellow, yellow's red, yellow or red, yellow or red, red, yellow, uh, orange, red, orange, and yellow or green. So the three states are yellow, orange. You're gonna have green, means something that's moving closer. You got the result, which can measure of a quantum state. But this is a magnetic triadic magnetic model. So you're gonna have pi over 4, and this means the north pole. You're gonna have pi over 3, pi over the pi over 3, which is east, pi over 2, which is south, and pi, which is 4, west. The sun rises in the east and sets in the west. So you can take a measure of the system that's topological consensual via plus. So I'm trying to take a measurement, given a measurement of a qubit, of a qubit, with an electron spin, use that to take a measure of electron, take a measure of electron, and take a measure of electron, and have that measurement be in another system, go to another system. So be in another system. So I'm just like a measure qubit and tell it and set set a qubit position two 2 qubits spinning to have isotropic relationship because basically they're gonna share quantum state, quantum just topological state. So when so one qubit sets a general qubit spin. So one would just set up. So basically, just reaching the position problem from the qubit to the velocity. So when an electron spins, one electron spins, party A spins, party B sets. So basically, the goes to have one half memory, and the conventional memory is as so if a quantum spin is an the third 3/2 of zero of one north of one a private through the third side is the third like PSI third pi over 3 the Russian number 3 of the Russian square root of 3 over 2 to the power 1 to 1 comma square root of 2 over 3 over over 2, basically it's a spin to north, east, and south, and west. There's some of the system. So because I have this model dimension, so the ratio of whatever the ratio is, the Russian number will be similar property of the sequence. So one study, I'm trying to map a quantum state via a linear graph in coloring. So I'm trying to color what would be. So I'm trying to take a cubic. So I'm trying to take a cubic. A qubit and have them have a configuration and determine the configuration topology of it of a cubic. What cubic looks like by using a bidimensional cubic. So that's what I'm trying to do. I'm trying to take qubits and like this is my work here now. So I'm trying to take a qubit and so for example square root of 3 over 2 to 1 and comma 3 over 2 over 3 square root of 2 over 3 divided by 2, and that's side. So side divided by and that's basically I have a conversion of a so basically to get conversion to get some noise or meaning from itself. So I'm going to tell me what is a meaning. Noise meaning there's no information, no noise. I mean no noise. I mean no signal when I'm connected to the system or this kind of system and signal. When I'm no noise, no. So it goes noise. These are those environments. No signal, and then I can't get connection. No noise environment. And signal when I'm getting meaning information from my computer system by measuring up by setting one qubit into another qubit by mapping the kind of spin. So the state you switch you should teleport the qubit. All the qubits should teleport. If party A is not teleport, the tomography should teleport. So it's a tomography computer model. Therefore, my so basically you have a shape of the spin and to give you meaning of the system. Let me try to do it to the AI system now. So let's see what the AI says about all of this. So basically, the AI should say something. What AI am I using? So, sorry. So there you go. To use pi over 3 and do that kind of problem here. So where is it now? Yeah, so so oh motherfucker. So answer. The Lorentz factor acts as a topological filter. So this answer is right. Basically, the Lorentz factor as a topological filter. That is the time window of the concept, allowing the bipartite consensus to reach by shielding spin memory from the current noise through relative time stretching. So should we formalize? Yes, please, yes. Author, author. You know, I want to see whether this is right. But but this model of quantum computer try to uh try bipartite students bipartite type so I'm not trying to say bipartite. So I know I'm right. Bipartite magnetic memory, magnetic memory, uh, quantum bipartite, quantum, quantum, quantum magnetic memory. Yeah, uh, via by via memory line. Yeah, temporal window, temporal type Fridays, census, maybe temporal. Via Illyria, Illyria, rough time, bipartite magnetic trident polarity, temporal, temporal polarity, uh, coherence, 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 coherence. Yeah, graph coloring, uh, red, fine, yeah, graph coloring, graph, coloring, the vertices, vertices. So I'm gonna give it graph coloring property, but basically it's a planarity and curve theorem. Planarity is a tendency graph, and it's a planar unilateral. Basically, it's a unilateral proof. Planarity can connect the graphs. It's a unilateral planarity consensus. So unilateral bipartite unilateral polarity is a planarity. Planarity. Uh, look like Nigeria. That's it. So let me print this page and just save it here. Oh, just save to OneDrive now. Save to PDF. Oh no. Oh no. So basically, I'm trying to save this work now. Save as PDF. Save as PDF here. Yeah, favicon. This is the planarity model. So you're gonna have unilateralism. You're gonna have you're gonna have chromatic polynomials. You're gonna have chromatic numbers. You're gonna have chromatic polynomials. So it doesn't matter whether it's a polynomial or not. You have a disjoint parent. So you're gonna have disjoint. You're gonna have disjoint. So you're gonna try to resolve the disjoint before you even write the color. So because there's that's what you should color it to just make sure you keep the disjoint. Just joking. But that's two ways to do it. Edge coloring, and basically edge coloring, node coloring, full coloring problem, coloring bipartite graphs, and basically I got this now. 14 minutes. This is gonna upload on TikTok now. So I'm gonna be done now because it's gonna upload on TikTok. So let me just give it to the AI system and work about it, and she'll be able to formalize it for me. Oh, upload an image, no, an image on the file. So then shift. New file command of I don't know. Basically, try something. This is the problem of BiPartite. You know what I'm saying? So I'm gonna copy this one. I'm gonna bypass it, combine this one. I'm gonna copy this one. Yeah, so so it has to be done properly. So I'm putting it in, but I don't like if I don't get a planarity proof now, I'll never get it. So let me get a planarity proof. So this is planarity. This is graph labeling and chromatic numbers. So chromatic numbers is like measuring current numbers like chroma keys, harness. So this is not good one. So I just wanna. I think I'll do it. Something wrong with the AI something. Oh my days. Stretch image. Okay, so let me try to do it now. I'll start my video now. 3, 2, wow, this is gonna 3 minutes ago, 3 minutes. Kind of routine. Go to, so basically, I just got a just take it from so yeah, let's start my days. Let's start this video now. So, it's really consistent.